Today's lesson is going to be on infinite limits, or limits that go to that are equal to positive or negative infinity. And so let's start off this conversation by looking at a function. F of x is equal to 3 over x minus 2. That is a rational function, and here's the graph of that function. If you notice, there is a vertical asymptote at x is equal to 2. Clearly, you know that the function is not defined at 2. If you substituted 2 into the function, you'd get 3 over 0, which is undefined. So it's not defined at 2. The function is not continuous either, but I digress. Well, let's talk about limits, though, in the context of asymptotes, vertical asymptotes in particular. If I ask you to tell me what the limit of my function as you approach 2 from the left, well, as you approach 2 from the left, so here's 2, and you approach 2 from the left, you'll notice that your function goes on without bound the negative direction. So this would be simply negative infinity. So my limit is negative infinity. If I were to ask you what the limit of your function is as x approaches 2 from the right-hand side, you notice that it increases without bound the positive direction. So this will be positive infinity. So both of these limits are infinity. One's positive and one's negative. Now, there is a correlation between infinities and vertical asymptotes. So whenever you have a vertical asymptote, you know that your limits are going to be either going to positive infinity or negative infinity. Now, be sure that you see that the equal sign of the statement, the limit of f of x is equal to infinity, does not mean that the limit exists. On the contrary, it tells you how the limit fails to exist, denoting that the unbounded behavior of f of x is x approaches c. So infinity, even though that's my answer, it's technically does not mean that the limit exists. It just explains why the limit does not exist. The limit does not exist because they both go into infinity. Remember, for a limit to exist, it has to be approaching an actual number, real number value. It's not in this case. But what I need you to get from this picture is that whenever your limits are equal to positive infinity or negative infinity, then you need to remember that there's a vertical asymptote here, or vice versa. If there's a vertical asymptote there, the limits are either going to be going to positive infinity or negative infinity. So let's take a look at some pictures. Or let's just talk about the definition about vertical asymptotes. So if your function approaches infinity, whether it be positive or negative, as x approaches some value c from the right or left, the line x is equal to c is a vertical asymptote. Another way of thinking about it is let f and g be continuous on an open interval containing the point c. If f of c is not equal to 0, g of c is equal to 0, and there exists an open interval containing c such that g of x does not equal to 0 for all x not equal to c in the interval, the graph of the function given by h of x equals f of x over g of x has a vertical asymptote at x equals to c. That was a lot to take in. I agree with you. So here's the main part. What you have to look for when you have a function is, of course, if it's a fraction, your denominator cannot be equal to 0. That's undefined. What this is telling me is that I will have a vertical asymptote for my function if the denominator is equal to 0 and the numerator is not at that point. In other words, if your denominator is equal to 0 for some value and numerator is not equal to 0 at that value, then you have a vertical asymptote at that value, at that point. And so let's take a look at some examples. It says find all vertical asymptotes. So for the first one, I know that I'm going to have a vertical asymptote. What I'm going to do is, by using that definition, I'm going to take the denominator and simply set that equal to 0. And if I set that equal to 0, I'll get x plus 1 is equal to 0, so I get x is equal to negative 1. So I get x is equal to negative 1. And I can't just assume that is going to have a vertical asymptote, because I have to test out the second part of that statement, is that the function, the numerator part, not equal to 0 at this value. Well, if you notice, the numerator is always equal to 1 for this function, so it's not going to equal. In other words, this is a vertical asymptote. So if I were to graph this, I would have a vertical asymptote at x is equal to negative 1. For the middle one, again, it's a fraction, so I do need to go ahead and take the denominator, set it equal to 0. Now be very careful when you solve this for x and you take the square root, you will get plus or minus 1. So it's not that you just have x is equal to 1, but you also have x is equal to negative 1 to test out. But you still can't assume that those are my vertical asymptotes without testing them. So plug each one of these numbers into the numerator, and see, I can plug it for this time because you have that x squared plus 1. If you plug in 1 into the numerator, you'll get 2. So that is a vertical asymptote. If you plug in negative 1 into the numerator, you'll also get 2. So both of those are vertical asymptotes. Keep in mind, again, in order for it to be a vertical asymptote, the function has to be wherever it is not defined, you plug it into the numerator, and as long as you don't get 0, then it's a vertical asymptote. If you get 0, then it's what we call a removal discontinuity. In other words, there's a hole there. We'll get into that a little bit later. The last one's a little bit tricky. You're probably thinking, well, it's not a fraction there. I ain't got to worry about that. Well, that's where pre-count comes in handy. If you remember, cotangent is the same thing as cosine over sine. So if I want to know where the vertical asymptotes were, you have a fraction now, so I need to know where is sine of x equal to 0. So again, sine of x is a periodic function. It starts at 0, it goes up to 1, then back to 0, then to negative 1, then back to 0. If you notice, there's a pattern emerging. There's a pattern at sine is equal to 0 at every pi increment. So in other words, at 0 plus pi k. The sine of x is equal to 0 at x is equal to pi k, every iteration of that. And cosine of x, so for that one, you can show that the asymptotes occur when x is equal to pi k, where n is an integer, because if you remember the graph of cosine starts at 1 and then goes to 0 and then to negative 1, then 0, then negative 1. And so you notice it's hitting 0 at pi over 2, then plus pi k. It repeats itself at 0 every single time. So it's not like these two things are going to overlap. So where is cotangent of x not defined? It's at all values pi k, where k is an integer, and so that's where my asymptotes of cotangent of x would be. Because if you plugged in cosine at pi is always, cosine at pi is going to give me negative 1. If you put in cosine of 2 pi, it's going to give me positive 1. So if you plug in cosine at pi, whatever, it's either going to be positive or negative 1. So not to worry about it ever equaling to 0 for the numerator. So therefore, those are my vertical asymptotes. All right, keep on going. Find all vertical asymptotes for this function. So again, start by taking the denominator and setting it equal to 0. And so then this gives me x squared is equal to 4. Then that gives me plus or minus 2. But again, you can't assume that those are my vertical asymptotes without testing each one. So let's test out the first one. And so if you plug in positive 2, you get 4 plus 4, which is 8. 8 minus 8 is 0. Whoa. So this one is not a vertical asymptote. It is actually what we call a removable discontinuity. In other words, it's a hole there. So that is not a vertical asymptote. I think we checked it. So now let's plug in negative 2. Well, if you plug in negative 2, 4 minus 4, which would be 0, then you get negative 8. So this is my vertical asymptote for that function. In fact, if you were to look at the graph, if you were to graph this, you would see that negative 2, there was a vertical asymptote, whereas at 2, negative 2, there is a vertical asymptote, and it kind of goes off like that. But then here, what happens is there's just a point discontinuity, it's a removable discontinuity right there. So definitely glad that you checked each one. Now, how does this relate to limit? Well, here it is. Let's say I wanted you to find each limit. So the limit as x approaches 1. specifically from the left-hand side. But if you notice, if you were to plug in 1 into this limit, you would get 1 squared minus 3 times 1 over 1 minus 1. You get 1 minus 3, which is negative 2 over 0. Don't let that get confused with determinant form. This is not in determinant form. This lets me know that, hey, I've got undefined value right there. In fact, if you want to prove it, look, if you take this function, x cubed minus 3x over x minus 1, if you take x minus 1 is equal to 0, and then solve it, you get x equal to 1. If you test that out, plug in 1 into the numerator, you get negative 2. You will see that x equal to 1 is a vertical asymptote. So in other words, at 1, I know that there is a vertical asymptote right here. The question, though, is, what is my function approaching as what is the limit of my function as I approach 1 from the left-hand side? Is it going to be negative infinity, or is it going to be positive infinity? Well, the best way to test that is simply pick a number that's close to 1 and plug it into the function, but I want a number that's to the left of 1. So in other words, a number that's less than 1. So I'm just going to simply pick 0.9. And so if I pick the 0.9 and plug it into the function, I'd have 0.9 squared minus 3 times 0.9 over 0.9 minus 1. Now, clearly in the denominator, I know that that's going to be equal to a negative number, because 0.9, and you subtract, that's definitely going to give me negative 0.1. The numerator, I'm going to use my calculator, so 0.9 times 0.9 minus 3 times 0.9 gives me a negative 1.89. And I could care less what the numbers are, I just care about the sign, because I know it's going to be infinity regardless. But negative divided by negative is a positive, so that's why I know that this limit is going to be positive infinity. Now, that doesn't mean the limit exists by any means. The limit does not exist if it's equal to infinity. That just lets me know that it's increasing without bound positive infinity. So that would be the limit right there. So, I could probably get an idea of the function basically doing this number right here. So that would be what the function is doing on the left-hand side. Now the question is, what's the function doing on the right-hand side? And that's what it's asking right here. What's the limit as you approach 1 from the right-hand side? Same function. So again, let's just pick a number that's bigger than 1. So I'm just going to pick 1.1. And so 1.1 squared minus 3 times 1.1 over 1.1 minus 1. Well, clearly in the denominator, 1.1 minus 1, that's definitely going to be a positive value. I can care less what that number is. Numerator, though, if I did this, I would end up getting a negative, again, a negative 2.09, but regardless of the number, I know a negative divided by positive is a negative, so that's why I know this limit, as you approach 1 from the right, will be negative infinity. So in other words, my function would be decreasing without bound as you approach 1 the right-hand side. So without even using a graphing calculator, I was able to determine some of this information just from vertical asymptote. And that's it for today's lesson.